to graph these pairs of functions. F of x equals log of x and g of x equals 10 to the x. Well, number one, let's recall what we talked about last time about notation for logarithms. So if we recall, y, so instead of scrolling back to the previous page, oh, come on. So y, oh, perfect. So y equals log base a of x. And again, or base b, actually we use b. Base b, where b is the base. And x, which is the expression inside of the parentheses. Well, I didn't put parentheses around the x because it's only one term. But we use those parentheses, well, depending on the needs, when we have more than one term. But I'm going to put it just for the sake of notation. And this is called the argument. All right. Well, so we were looking at two particular cases. The LOG without any subscript. So let's see if anyone remembers. What's the number that we are supposed to understand that it's there when we don't see any number? It's a base 10. It's also known as a common logarithm, right? Or base 10 logarithm, or simply logarithm. When we have the ln, that's another special logarithm. It's a logarithm, log base e, all right? And I think you can see where are we going with this. Well, log base 10 and 10 to the x. Well, a few times already I talked about how logarithmic functions and exponential functions are inverses to one another. Well, this is what we're going to do now. We're going to graph these two functions together and, well, you'll see what's going to happen. So, okay, log x, and this is what I'm going to do. I'm going to type the number 10 and erase it to the 10th power. I mean to the x power. So that's the two pairs of functions, and I'm going to click the graphing button. All right. So here's the thing as well, guys. So notice we were supposed to get some graph like keep going down to negative infinity. But again, that's something we also talk about graphing calculators. They're not very, very smart devices. They're not going to show you all the details actually. So again, it's important to know, to take into consideration those asymptotes, whether they are vertical or horizontal. And, oh my God, it's me open the door. Kind of need fresh air. So notice how we can trace a diagonal line here, all right? And when we do that, let me type the equation of the diagonal line, and that's basically the equation of y equals to x. However, I'm going to type that equation, okay, y equals to x, but I'm going to do that dashed so you can see something. I think this one is fine. Okay, and I'm going to, oh, okay. I didn't click enter. Okay, so that's a line. Okay, click OK. And graph. This you can see something. Well, you can see that the graph in blue is a reflection of the graph in red. Well, however, due to the aspect ratio of the screen on the graphing calculator, it doesn't look perfectly symmetric. However, if you did the calculations or the plotting points by hand, you would obtain a perfectly symmetric pair of graphs in this case. So that's another limitation graphing calculators have. On the other hand, you know, when you want to graph a circle, for example, it's not going to show you a circular shape. Essentially, it's going to show like an ellipse. So, and that's again because of the aspect ratio of the graphing calculator, the screen rather, notice how the x's are more stretched than the y value, so that's why we wouldn't see this perfectly symmetric. But trust me, they are perfectly symmetric. Okay. Now we're gonna draw the graph of ln of x and e to the x. Well, in this case, we have an exponential function base e. So its inverse, we would expect it to be a logarithmic function, but in this case of base e. So let's go ahead and replace. I'm going to replace this with ln, and we have a dedicated keystroke for ln. It's right here next to the number 4. And if you want to do the inverse exponent, the natural exponential, the e to the x function, stick to the ln keystroke here. However, you will see the e to the x in blue. In order to reach that function, press the blue button, the second, and that's going to give us the e. And then it's going to open a box for us to type the variable. And I'm going to leave this graph of x. I think I should have used the other version of it. And graph. Much better, right? Looks more like asymptotic. So, and again, they look similar. So ultimately, some pairs of logarithmic and exponential functions may look steeper than others. That's going to depend on the base of the exponential that we use, So, and you can see that when you graph other pairs of, an exponential function and a logarithmic function of the same base. However, something to be careful here. Notice this. Notice I only chose 2 examples. The example on the base 10 and the example on the base e. Can we graph logarithmic functions on other bases? Well, we can do the exponential. That is fine, because we can raise 2 to the x and 5 to the x. It's easy to do on the graphing calculator. However, if you look at the graphing calculator here, notice we only have keys to evaluate logarithms, base 10, and natural logarithms. We don't have a key to evaluate, say, a logarithm of base 2, a logarithm of base 7, base 5, just directly. However, if we wanted to do that, some calculators, not all of them are, unfortunately. So if I want to draw another pair, okay, let me clear and clear. I'm going to draw the pair 5 to the x. We can just use the exponent key, and that's going to be our 5 to the x. However, we would have to type a logarithm base 5 function, which again, some of the older calculators don't have that function. The newer calculator, the newer versions actually do. And to do that, we go, where is it? We go math. We're going to go num. And I'm going to scroll up to reach the last. Is it this one? No, it's not this one. It's math. And okay, log base. This is the one I'm looking for. Not all the calculators have this log base function here. The minute I type it, it's going to type me a log, a subscript, and then open parentheses for the argument. So I'm going to start with the base. Well, since in this case I'm using a logarithm of base 5, an exponential base 5, I have to type a logarithmic function of a base 5 of x. And same. All right. Same picture, same symmetry. Again, it doesn't look as well. It doesn't look that well due to the aspect ratio of the screen here. All right. Now, the problem here is that some of you may have the log base function on your calculator, some of you may not. Well, how do we do that in case we don't have access to that function? Well, we're going to in the next section, we're going to learn a formula called the change of base formula, in which we're given a logarithmic function, say base 7, base 9, base pi, base square root of 3, for example. That one we cannot evaluate it in the calculator, but when using the change of base formula, we change that logarithm into a base either 10 or natural logarithm, which we can easily do in the graphing calculator. But that's something we're going to discuss in the next section. So in the meantime, well, so I really wanted to see you guys why did we start with one-to-one and inverse functions, because that was the very foundation to describe the relationship between the exponential function and the logarithmic function. And that is, well, back then in general, we saw that graphing the two functions, a function and its inverse, we get some symmetry about the origin in this case, right? About the line y equals to x. So in the particular case that we wanted to do for our purpose, rather is logarithmic versus exponential. All right. Now let's do some algebra to find the inverse function here. Well, so number one, we have some f of x equals 3 times log of x minus 1. All right. So we're going to go back to the process of finding the inverse function. That is number one. If you're given f of x, which most likely you will be given, so first we need to change our f of x with y. Now, to get the inverse function, here is where we invert the variables. That is, we interchange x's with y's. So y becomes x, and x becomes y. And then from here, we solve for the y variable. So we need to isolate the y, but there's a couple of things that we need to worry about first. Number one, we have a 3 multiplying there, and we have a logarithm that we need to rewrite. So let's see what about it. So I'm going to divide both sides by 3 to leave us with log of y minus 1 equals to x over 3. Okay? So that's to begin with. And well, we're a couple of steps away to get the y by itself. However, up to this point, I haven't taught you the property to cancel logarithms with exponentials or vice versa. And that's something we will learn, I think, in the next topic in the same section at the end. So far, we have discussed how to go from logarithmic form to exponential form. That is, let's see, log of x on the base a equals y, because what was the definition? That's a to the y equals to x. That's how we go back and forth between exponential and logarithm. So we're going to apply the same idea to this statement right there. So, but well, again, I wonder what the base is. Notice the base is sort of invisible. We know, so when we don't have any subscript here, it's supposed to be understood that it's a base 10. So that means I'm going to write 10 to the x over 3 equals y minus 1. All right, that's by definition of going back and forth between logarithmic and exponential expression. All right. From here, well, we're only one step away to get the y by itself. Just add 1 and cancel. And that's going to give me y equals to 10 to the x over 3 plus 1. And we will think we're essentially done, right? I mean, we're essentially done, but not quite done. We just got y equals that inverse function. We need to do one more step, which in this case is use the correct notation, because indeed, yes, this is y, right? And this new function, which comes from the same function essentially, is also y. So if I say y equals this and y equals that, I'm saying that these two quantities are the same, which are not. Actually, the last result we obtained here should be denoted f inverse, because we're looking for the inverse function, right? Final answer. Let's look at the next example. Okay. So we have another logarithmic function for which we want to find its inverse. So whenever we are giving a logarithmic function and they ask us to find its inverse function, we can sort of already envision that our end result will be an exponential function. Well, so number one, let's identify the base of the logarithm. What's the base of the logarithm in this case? It's base e. It's a natural it's a natural exponential, which is the base of this logarithm. And well, first things first, change g of x with y equals to ln of x plus 4 and minus 5, of course. And in this case, make sure to make sure to be the next step the interchanging of the variables. That is, make this an x, ln of y plus 4 and minus 5. And again, in a similar way that we did with the previous example, our goal is to isolate y. Once we do these algebraic manipulations, then change its notation and give it its own name called f inverse. All right? So let's go ahead and do that. Add 5 to both sides. So that's ln of y plus 4 equals to x plus 5. And again, we have a definition to go between logarithmic and exponential. Right now we are still getting used to, this is supposed to be a 5. We're still getting used to the definition, to the fact how we go back and forth. But once we get into the inverse properties, it's going to be a lot easier. And from then on, we are going to apply that to simplify expressions and solve equations. You'll see. Well, to go, so ln, which is the same as log base e, that means y plus 4 equals to e to the x plus 5. Right? That's because the subscript becomes the base and the argument becomes the equal part. All right? So, and then let's just solve for y by subtracting 4 on both sides. That's e to the x plus 5 minus 4. And again, let's make sure to denote that y as an f inverse of x. E to the x plus 5 minus 4. And I mean, you can always check the consistency of the work we did, because, well, we started with a natural log. That means log base e. So our end result, which is an exponential function, has to be the same base as the base of the logarithmic function, which in this case is base e. And now we're going to start with an exponential function. Well, what's the inverse of an exponential function? In general, not this particular. So if the inverse of a logarithmic function was an exponential, what would be the inverse of an exponential? Logarithmic, right? So that's what we have to do in this case. Well, so okay, first things first, y equals to 4 to the x minus 5 plus 3, and interchange x's with y's. And well, now that we interchange x's with y's, now we want to solve for y. So let's isolate the exponential term first. I'm going to subtract 3 on both sides. For y minus 5, wait. 4 to the y minus 5. Well, it's a little noisy outside, so close the door. And so yes, so 4 to the y minus 5 equals to x minus 3. Now we're going to go from exponential to logarithmic. So in the previous couple of examples, we went from logarithmic expression to exponential expression. Now we're going to go back. We're going to do this process backwards. So in this case, this x minus 3 will be the argument. This 4 will become the base of the logarithm, and this will be the y value, if you will. So y minus 5 equals log base 4 of x minus 3. And we're only one step away to get the y by itself. Just add 5 to both sides to cancel. Negative 5s and get the y by itself. So log base 4 x minus 3 minus 5. And again, notation matters. We're not just getting another random y function. This function is this y function though is very, very special. It's a very special one. It should be treated as such, which is the inverse function. Log base 4 of x minus 3 minus 5. Sounds good? What's next? Okay, yes, basic properties of logarithmic functions. That's precisely what I was talking about, how these functions are inverses to one another. So from here on, we will no longer be required to write the statement between logarithmic and exponential, or vice versa, in order to do whatever computation or calculation required. All right. So what do we have as as basic property? Number one. So whenever we want to evaluate a logarithm of a number, say this number, and if this number, the argument matches the base of the logarithmic, essentially they cancel out, and this is equal to 1. Well, to justify that, how about we use what's it called? The equivalent form. That means b to the 1 equals to b. I mean, if we use the definition of going back and forth between exponential and logarithmic, so that means this logarithm is the power of the base whose results into the argument of the logarithm. And we can see that b to the first power, isn't it just itself b? Let's look at the second property. So logarithm of the number 1, regardless of the base, is always 0. Log of 1 equals 0. Log of 1 base 7 equals 0. Log of 1 base 4 equals 0. ln of 1 equals to 0. Well, to justify this, this result of a logarithm is the exponent. We have to raise the base so that we get its argument. That is, b to the 0 equals to 1. And do we agree that b to the 0 power equals to 1? I mean, any quantity to the 0th power is 1. Okay? The last couple properties, those are like the two main tools that you want to use that we want to use for what it's next. All right, so let's see. Whenever we have an exponential function evaluated at a logarithmic function for which the bases match, essentially check this out. Essentially what happens, the log b cancels the exponential b, and the result is x. Likewise, when we do the, evaluation in the reverse order. That is, we evaluate a logarithmic function at an exponential function. Well, this exponential cancels the logarithm as long as the bases match, and surprise, they go back to the same. Now, the question is, where does that come from? Well, it all stems from this idea. You might remember from, well, I think this is the part you watch on video. Whenever we evaluate a function, let me make some space. F of x bubble with f inverse, that equals x. When we do the composition of a function with its inverse, what happens in this case? Well, it goes back to the original function, and the reverse order for this is true. Well, actually, another way to denote for like a composition, that's f evaluated at f inverse of x equals to x. Okay? Essentially, if you will, you can, okay, this is actually not legit notation, but I mean, but this is something like just to like think of. So essentially, f cancels its inverse, and the result is x. But this is not the right way to do the thing. You know, it's one way sort of interpreting, and well, the order has to go the other way around as well. The other way around, that's f. Of x, or f inverse evaluated. This bubble, this circle, that doesn't mean multiplication. It actually means composition, and that's also x. In other words, f inverse gets evaluated at its original function, and that equals x. And you might recall how we proved, well, not really proved, how we actually check for the consistency of this result when we did an example with a cubic radical and with a cube root function and a cubic function. We got the inverse, and then we showed on that video what you saw on that video is how composing the functions or evaluating the function at its inverse, the result is x. So same thing is going to happen with these logarithms and exponentials. All right, let me get rid of this because I need to write more stuff over here. So there's actually some restrictions to these two properties. One, this is for all x in the real numbers. There's no restrictions for the domain. This upside down A means for all. And this little E means belongs to, you know, like when we write the domain of a function, you know, belongs to all real numbers. So no problem with this. However, there is a restriction with using the second statement here. And if you think about the logarithmic function, because that's the function that we evaluate first, you know, order matters when doing the composition. So in this case, we're evaluating logarithmic first. So we need to take the domain of the logarithmic function into consideration. And well, this is in this case for x greater than 0, because that's the domain of a logarithmic function. Only values of x that are greater than 0, not including 0, not including negative numbers. So for now, right? Again. Okay. Find the exact value of each logarithm without using the calculator. All right. Well, and if the minute you see this first exercise, you might think, well, we already did that at the beginning of the section. In fact, yes, that's how we started in order to see the going back and forth between logarithms and exponentials, so we can explain that the base, so that the logarithm is the exponent that we need to raise certain base in order to get the logarithm's argument. So what we did here, here this turns out to be a 2 because 8 to the second power equals 64. That's what we did at the beginning of the section. But today we're going to use properties of logarithms here. So this is what we want to do. I'm going to take advantage of this property right here, to cancel a logarithm with an exponential. Okay? But in order to get that done, we need to get a match between between the base of the exponential and the base of the logarithm. So in this case, well, we don't have an exponential in our argument. It's only a number. It's only an integer. The number 64. How is that an exponential? Well, so here our goal is to write the number 64 as a power of the number 8. So I'm going to write log base 8, all right? And well, is there a way to write the number 64 as a power of 8? And if so, what's that? Anyone? 8 squared, okay? So 8 to the second power. And now check this out. See how the base of the logarithm matches with the base of the exponential? Only then we can cancel. Notice this time I'm not using the going back and forth between exponential statement and logarithmic statement. And once we get this canceled, the final result is 2. All right, let's look at letter B. For letter B, same situation, same thing. However, we may need to do a couple more manipulations before we can actually find a match between the base of an exponential with the base of the logarithm. So observing these numbers right here. So notice that 36 is in the denominator. Well, we'll take care of that in a second. Now, the question is, can we write the number 36 as a power of 6? And I guess that's pretty straightforward. That's the same as saying 1 over 6 to the second power. All right? Now, careful, because we cannot cancel just yet. Because that 6 to the second power, it's in the denominator. And in this case, essentially this b to the x is like saying b to the x over 1. So we need to have that to the numerator. But we can use laws of exponents to fix this. And write this as log base 6 of 6 to the negative 2. And now it looks pretty much like this property right here, for which we can just cancel the log base 6 with the exponential of base 6, leaving us with a number negative 2. All right? Let's see what else do we have about this. Okay, log of 1 on the base 9. Logarithm of the number 1 regardless of the base equals 0. Just that. That's all we need. 0. Okay. Log base 3 of 9 to the negative 1. Well, I know there's kind of a lot going on in here. So we have base 3. The minute we see the number 9, we can already think of writing the number 9 as a power of 2. But we have that negative power kind of trying to throw us off. So let's see, what do we do about it? So you might remember one of the properties of, or rather laws of exponents, that say, the one that says a to the m. It's not necessary. It's more like an intuitive idea. This is the same as a parentheses m, right? Because essentially this is a to the first power, if you will, and 1 times m equals to m. So what I'm going to do here is write this 9 to the negative 1 as log base 3, 9 to the negative 1. And now I'm going to work with the number 9 by itself. And well, log base 3 of 9, not 9, actually this is 3 to the second power to the negative 1. Okay? So now we are getting somewhere. We're getting to the fact in which, or we're getting to the point in which the base of the exponential matches the base of the logarithm, but not yet. We need to simplify these exponents, and the other law of exponents that we might want to use here, which is similar to this one, a to the m times, to the n, power of another power, powers multiply. All right, that's what we're going to do here. 2 times the negative 1 log base 3 of 3 to the negative 2. I know I'm going at a very slow pace. If you think I'm going at a very slow pace with going back to the really basic definitions, there's a purpose behind this, because later we're going to look into examples with more intricate numbers, with funkier numbers, and in those situations it may not be easy to see all this behind the scenes. So you'll see when we get to those funkier cases. So the reason to this is again to sort of prepare to those. Now, okay, we can cancel log base 3 with exponential base 3. And final answer, negative 2. Letters E and F deal with inverse functions, with compositions of the function and its inverse. So in this case, what do we have? We have an exponential being raised to a logarithm. So in this case, well, let me go back to the previous page for a minute. All right. So these last two properties, let's label them A, B, C, and D, so to speak. Well, the letter C shows the composition between a logarithm and an exponential, while letter D shows the composition between an exponential and a logarithm. So in this case, again, the bases of the logarithm and the exponential have to match in order for us to be able to canceling them, and vice versa for the other order. Let's see if it is the case for letter E. So what do we have? E to the ln of 3 for letter E. Again, what's the base of ln? It's base E, so that means we can simply do that. And final answer, 3. Now we have the composition between a logarithm and an exponential. Well, in this case, the ln, which is a log base E, matches with the base of the exponential. We can cancel this down like this. We can cancel out like this. Or if you would like to be more explicit about it, you don't have to. It wouldn't hurt to do this, but it's not required. So again, these are one of those understood or things we take for granted when we see ln versus E or E versus ln. Just wipe them out. Final answer, 35. Okay. What about letter G? Well, for letter G, we don't have E and ln. Nevertheless, we have an exponential and a logarithmic expression. We have a combination of the both. We have a composition, rather, of both. In just the same way that we look for the base of the logarithm to match the base of the exponential on the previous couple of examples, we have to do the same here. Well, what's the base of the exponential? What's the base of the logarithm? Can we Wipe this out? Yes. Final answer, x minus 5. That's it. What about letter H? We have an exponential base 10. And we have a logarithm apparently with no base. But again, when we don't see anything typed in the subscript, what is supposed to be understood to be the base? So it looks like we have a match between the exponential, the base of the exponential, and the base of the logarithm. That's 3x minus 11. All right, and the argument can be anything. Well, again, for variables, just make sure to have x greater than 0. But well, that's all right. What do we have? What's this funkiness here? Log base 13 of 13 raised to the log base 13 of 13 to the x to the 13. All right. Yes, as far as this may look a little scary, how about we do one cancellation at a time? And this one, it's going to be pretty straightforward because if you observe the larger numbers, which are actually the exponential, the exponentials, they really do match with the base of the logarithm. So on the first instance, we can actually cancel log base 13 with the first exponential, with the first immediate exponential, all right? That's going to leave us with the following. That's going to leave us with log base 13 of 13 x of 13 to the x to the 13. I know, powers of powers of powers, kind of big. But again, log base 13 of 13, we have a match between the bases of the exponential and the logarithm. Cancel, cancel. That's going to lead us with x to the 13. And the last one. Oh, that's not the last one yet. Letter J, log of the cube root of 100. Well, I think we did something like this back when we covered the definition on between exponentials and logarithms base 10, when we did a few examples. But no, I don't think we did this one. But again, now the question here is, well, actually, the cube root of 100 may not be an exact number, may not be an integer. So at first glance, it may be hard to think of writing the cube root of 100 as a power of 10. However, we can write radicals as rational exponents and then do some manipulations to the number 100. Well, in the first place, this is log base 10. Oh, no, not base 10. Base 1, log of 100, base 10, the one that we don't need to write. And this 100, can't we rewrite it as to the 1/3? Again, because the index of the radical tells us the denominator of the rational exponent. That's how we go between radical form and rational exponent form. All right, now, our goal is to write, okay, let's focus on the number 100. Yes, the radical, it's kind of a funky number to write it as a power of 10 because it's weird. However, let's focus on the number 100. Can we write the number 100 as a power of 10? What's that number? 10 squared, that is 10 to the second power, and that raised to the 1/3 power. Well, we are almost there as far as canceling the log with the base 10. However, we still need to simplify the multiplication of the exponents here. Power of another power, just multiply the powers. That's log of 10 raised to the 2/3, and voila, we can cancel these to 2/3. All right.